Let's jump right into this explainer. Today, we're unpacking an entire chapter dedicated to an absolute workhorse of computer science, the stack. When we use our devices, we just expect them to remember our actions, crunch complex math, and keep software running without a hitch, right? Well, beneath all that seamless magic lies a beautifully elegant data structure that makes it all possible. We're going to demystify how a simple, physical concept translates into code. Here's our roadmap for this explainer. We'll start with the LIFO principle, look at some real-world applications, break down push and pop operations, write some Python code, and finally, check out prefix and postfix notations before converting infix to postfix. Section 1, the LIFO principle. Let's start with the absolute basics of how a stack is actually put together. Think about a literal stack of books on your desk. If you want to add a new book to the pile, you just plop it squarely on top. Want to remove one? You grab the top one. Trying to pull a book from the very bottom or the middle? Yeah, that's just asking to topple the whole thing over. It's super inconvenient. In computer science, we organize data elements in this exact same linear order. It perfectly mirrors a pile of plates or books where you only interact with the top. Which brings us to the formal definition of this behavior. LIFO, or last in, first out. It's elegantly simple. The element inserted last, the absolute newest piece of data, will always be the first one taken out. The whole structure restricts us to interacting with just one single end, which we intuitively call the top of the stack. Section 2. Real-world stack applications. So why does this actually matter? Where do we use this invisible pile in our day-to-day digital lives? Well, every single time you hit the back button on your web browser or undo a typo in a document, you're navigating a stack that the software built entirely behind the scenes. Think about it. If you surf from web page 1 to page 2 and then page 3, your browser stacks them up. Clicking back pops page 3 off the top, right? And boom, there's page 2. Stacks are absolutely everywhere. They're used for reversing strings of characters, and even by compilers to check if the parentheses in your code are properly matched and nested. Moving to Section 3, push and pop operations. Let's look at the actual mechanics of how we manipulate this thing. It all boils down to two fundamental operations. Pushing adds a new element onto the stack, and popping removes it. These actions are constantly shifting that top position. Push is strictly your insertion operation. You're slapping a new element right on top. Pop is your deletion operation, grabbing whatever is currently sitting up there. And because we only ever mess with that top position, these operations are incredibly fast and efficient. But, we do have to be careful. Just like you can't grab a plate from an empty table without just grasping at thin air, trying to pop from an empty stack throws what's called an underflow exception. There's just nothing there to grab. On the flip side, if a stack has a fixed memory size and you try to push an element onto it when it's already full, you trigger an overflow exception. All right, Section 4, coding stacks in Python. Let's take what we've learned and build it into actual code. The great news here is we don't need some complex new tool. Python is awesome because it lets us use its standard list data type to act as our stack. By simply fixing one end of the list to be our top, we mimic that LIFO behavior flawlessly. To get started, we literally just initialize an empty list, which we've named glassstack. Then, to replicate our push operation, we just use the built-in append method. This perfectly places the new element right at the tail end of our list. And because Python lists automatically expand in memory, we rarely have to stress about that overflow exception we just talked about, unless your entire machine completely runs out of memory space, which is a much bigger problem. Similarly, Python's built-in pop method cleanly mimics our stack's pop operation. It just slices that last added item right off the top. Of course, if you were writing a complete program, you'd want to toss in a quick check to ensure the list isn't empty before running this. You definitely want to avoid accidentally triggering that underflow exception. Section 5, prefix and postfix notations. We've built our tool, so let's see how it solves a genuinely complex problem, helping a computer evaluate math. As humans, we read math as infix expressions using BODMAS rules, right? But computers, they strongly prefer prefix or postfix notations. Why? Because repositioning the operators entirely removes the need for clunky, confusing parentheses. This brilliant idea traces all the way back to the 1920s with Polish mathematician Jan Łukasiewicz. By placing operators either before the operands, which is prefix or Polish notation, or after the operands, which is postfix or reverse Polish notation, the order of operations is baked right into the positioning.
A computer can just read a postfix expression smoothly from left to right, 0-second guessing required.
Section 6. Converting infix to postfix. The crucial point of this chapter is figuring out exactly how we translate human math into computer math. And this is exactly where our stack shines. We're going to methodically step through this conversion algorithm. We'll read the human equation from left to right and use a stack to temporarily hold onto our operators and parentheses. All the while, we'll steadily build a brand new string called postx, which will be our final computer-friendly postfix answer. Okay, here's how the rules play out. When we hit a left parenthesis in the equation, we just push it onto our stack to save it for later. It basically acts as a bookmark. Now, if we hit a standard operand, say a number, or a variable like x or y, we completely bypass the stack. We just append it straight onto our output string. Now, this is where the real magic happens. The stack manages the BODMS precedence rules by forcing higher priority operators off the stack and into the final string before a lower priority operator is allowed to be pushed. For example, if you try to push a plus sign onto the stack, but there's a multiplication sign already sitting at the top, that multiplication sign gets popped right off and added to your output string first. The stack demands strict order. Finally, hitting a right parenthesis triggers a total cascade. It starts popping all those carefully stored operators out into our finished postfix string until we hit that original left parenthesis marker we dropped in earlier. Once the entire expression is read, we just pop whatever operators are left in the stack and append them to the string. The result? A perfectly formatted equation that a computer can evaluate in one single, blisteringly fast pass.
So, we've seen how stacks manage our web history and evaluate complex math. But what other invisible piles do you think are holding your digital world together? That wraps up our explainer on this incredibly versatile structure, and it definitely leaves you wondering about the other hidden data architectures powering our screens. From tracking the active functions in your operating system's memory to powering the undo button when you make a typo, that last in first out pile of plates is quietly doing the heavy lifting. I highly encourage you to test yourself by explaining this chapter's Python script on your own. Go on, start experimenting with pushing and popping your own data.